Hello everyone, welcome back to my way. Let's look at a practical example. Imagine a satellite internet gateway. The satellite is transmitting two independent communication channels, one using RHCP and the other using LHCP. Both signals arrive at the ground antenna at the same time. The polarizer converts the circular polarization appropriately, and the OMT separates the two polarization states into two independent RF paths. One output carries the RHCP signal while the other carries the LHCP signal. Two receivers can then process the signals simultaneously without interfering with each other. This is one of the biggest advantages of combining a polarizer with an OMT. Satellite communication is not the only application. These components are also widely used in radio astronomy, where scientists observe celestial signals with different polarization states. Deep space communication, where spacecraft orientation changes continuously, making circular polarization the preferred choice. Weather and surveillance radar, where polarization helps distinguish different types of targets. Electronic warfare and signal intelligence, where receiving multiple polarization states improves the probability of detecting unknown signals. Antenna measurement labs, where engineers characterize antenna performance under different polarization conditions. So when should you choose each type? If your system always requires the same polarization, for example only RHCP or only LHCP, a fixed polarizer is the simplest and most reliable solution. If you need the flexibility to switch between linear RHCP and LHCP, an adjustable polarizer is the better choice. It's commonly used in labs, research, and antenna testing, where different polarization states are required. And if your application needs RHCP and LHCP simultaneously, such as in satellite ground stations or dual polarization communication systems, then the ideal solution is a polarizer combined with an OMT. So to summarize, fixed polarizer, best when polarization is required permanently. Adjustable polarizer, best when you need to switch between linear RHCP and LHCP. And finally, polarizer plus OMT is the best choice when RHCP and LHCP are needed simultaneously through a single antenna. Now that we have understood how polarizer and OMT work, let's talk about how we evaluate their performance. Let's start with polarizer. There are several important RF parameters that we test for a polarizer. The first parameter is frequency bandwidth. A polarizer is designed to operate over a specific frequency range. For example, a polarizer may be designed for 40 GHz to 50 GHz. An important point to understand is that polarizers are inherently bandwidth-limited components. The bandwidth is affected by the design of the polarizer itself and also by the waveguide structure used. Most millimeter wave polarizers use circular waveguides, and circular waveguides have their own operating bandwidth limitations due to waveguide modes. As frequency increases, additional waveguide modes can become excited, which can affect polarization performance and create unwanted mode conversion. Therefore, the usable bandwidth of a polarizer is limited by circular waveguide operating bandwidth, polarizer geometry and design, higher order mode control, and required axial ratio performance. Because of these limitations, polarizers are typically designed for specific frequency bands rather than extremely wideband operation. The second parameter is insertion loss. Insertion loss tells us how much RF signal power is lost as the signal passes through the polarizer. For a circular polarizer, insertion loss is measured at different polarization orientation, RHCP position and LHCP position. The difference between these two insertion loss measurements is used to calculate the axial ratio. For example, at 30 GHz, insertion loss at RHCP position is 0.5 dB. Insertion loss at LHCP position is 1.5 dB. The difference is 1.5 dB minus 0.5 dB, which is equals 1 dB. This difference represents the axial ratio performance of the polarizer. The smaller difference means better circular polarization purity. For perfect circular polarization, major axis is equal to minor axis. Therefore, axial ratio is equal to 1. Let's explain axial ratio in simple terms. An ideal circularly polarized wave has equal electric field strength in two perpendicular directions. The electric field rotates and creates a perfect circle. In a real polarizer, the two orthogonal components may not be exactly equal. Instead, the electric field forms an ellipse. The axial ratio describes how close this ellipse is to a perfect circle. The axial ratio is defined as axial ratio is equal to major axis by minor axis. For perfect circular polarization, major axis is equal to minor axis. Therefore, axial ratio is equal to 1, or in decibels, it is 0 dB. The closer the axial ratio is to 0 dB, the better the circular polarization performance. One important point about polarizer testing is that the true VSWR of the polarizer itself is difficult to measure directly. The reason is that the polarizers usually require waveguide transitions or adapters to connect them to measurement equipment. These transitions introduce their own reflections and losses. Therefore, the measured VSWR includes the effects of polarizer, circular to rectangular waveguide transitions, adapters, and measurement setup. Because of this, the measured VSWR is not a true representation of the polarizer alone. For this reason, polarizer characterization focuses more on frequency bandwidth, insertion loss, RHCP, LHCP isolation, and axial ratio. Now let's talk about how we test OMT. An OMT has 3 ports, as we all know now, 1 circular waveguide port and 2 rectangular waveguide ports for the 2 orthogonal polarizations. The main goal of the testing is to verify that the OMT efficiently separates these polarization channels. The first parameter we test is frequency bandwidth again. An OMT should maintain good RF performance across its entire operating frequency range. Traditionally, the bandwidth of the waveguide components has been limited by the waveguide design and higher mode effects. However, with advanced OMT designs, wideband performance is now possible. For example, we offer wideband OMTs covering 18.5 to 31 GHz, 26.5 to 40 GHz, and 33 to 55 GHz. The second parameter is insertion loss. We measure the signal loss from the antenna port to the vertical and horizontal ports. Lower insertion loss means better RF efficiency. The third parameter is return loss. This tells us how well each port is matched and how much signal is reflected back. Good matching ensures efficient signal transfer. The most important OMT parameter is port isolation. Isolation measures how well the OMT separates the 2 polarization channels. For example, a signal entering the vertical port should have minimal leakage into the horizontal port. The typical OMT measurements are performed using a vector network analyzer measuring insertion loss, return loss, port isolation, and phase response. In summary, the key OMT parameters are frequency bandwidth, low insertion loss, good return loss, and high port isolation. Here is one interesting part. Do you know that only circular waveguide antennas are used for dual polarization by connecting OMT and polarizer? When a circular waveguide feed antenna is connected directly to an OMT, it becomes a dual linear polarized antenna, supporting both vertical and horizontal polarizations simultaneously. If the same circular waveguide feed antenna is connected to an OMT through a circular polarizer, it becomes a dual circularly polarized antenna, supporting both RHCP and LHCP simultaneously. This is possible because a circular waveguide supports 2 orthogonal polarization modes, allowing the OMT to separate or combine them into 2 independent RF channels. In contrast, a standard rectangular waveguide feed antenna supports only a single dominant linear polarization mode. You can physically rotate the antenna to change the polarization from vertical to horizontal, but it still supports only one polarization at a time. It cannot be converted into a dual polarized antenna using an OMT or a polarizer. In addition, both the OMT and the circular polarizer are designed with circular waveguide interfaces, making them compatible with circular waveguide feed antennas. If you're interested in dual polarized antenna solutions for satellite, radar, or millimeter wave applications, explore the dual polarized antenna products available on our website. Understanding the differences between fixed polarizer, adjustable polarizer, and OMTs helps engineers select the right solution for their specific applications. So, the next time you look at a satellite antenna, radar system, or millimeter wave communication link, remember that there is much more happening than just sending and receiving signals. Behind that antenna feed, components like polarizers and OMTs are quietly controlling the direction, rotation, and separation of the electromagnetic waves, allowing multiple signals to travel through the same piece of hardware with precision. A small change in polarization can decide whether a communication link works perfectly or suffers from interference. That is the power of polarization engineering. If you enjoyed this explanation and want to learn more about the hidden technology behind RF and millimeter wave systems, subscribe to our channel. In our upcoming videos, we will continue exploring the world of waveguides, antennas, filters, frequency converters, and other technologies that make modern communication systems possible. Thank you for watching and see you in the next RF journey.